Okay, so this chapter is about interacting system. You know, I mean, generally every system is interacting with its environment. You're interacting with the chair, you know, which is preventing you from falling down and all that kind of stuff. Yep. So we adapt to our environment. Yep. So living organisms evolve and adapt to make most of their interactions with their environment. Okay. So you adapt to your environment and you do the best you can in the given environment. So for instance, see, you will learn, here are plants that grow underwater. What's the difference between these guys and plants outside? See, they don't, because they're underwater, you learn that they have buoyant forces acting on them, counteracting gravity. So structurally, they don't have to be as strong. So for instance, if you planted this outside, it would essentially collapse. The wind would blow it away and all that kind of stuff. So they don't need as much cellulose. So plants, animals that live in water have different body plans and structures, yeah, because of the different forces and stresses. So our goal is understanding how do you adapt to the constraints that are put on you. Okay. So for instance, here is a paramecium that lives in water. This is essentially like if here in the paramecium, the viscous forces of water, viscous forces essentially is friction exerted by liquids. So this would be the same as if you had to live in a pool of honey. So if you had to move in a pool of honey, you can't swim in a pool of honey. You got to figure out a way to move. Okay? So we want to understand the constraints that physical environments place on creatures. And so that's what we're going to study. Okay? So the motion of a swimming paramecium is dominated by viscous drag forces. Okay? So you will we'll see that it has a flagella. These are cilia, and there are single-celled animals that have flagella that will help them move. You got to keep pushing, and the instant you stop pushing, you stop. Okay? There's no coasting there. So we'll learn how they adapt to the environment. Okay? So here's a kangaroo that hops. Okay? And we'll understand. We'll talk about this. Now, before I do that, let me show you a graph. Okay. So what this graph shows, this should be rate of energy consumption. This is speed. This is a very interesting graph. See, for a normal mammal, as you run faster and faster, your rate of energy consumption increases. Look at the graph for a kangaroo. Okay. It's essentially flat. It's running faster and the rate of energy consumption hasn't increased. So my question to you guys is, why aren't we all hopping instead of running? What's that? Yeah, well, why didn't you evolve structures to hop rather than run? I mean, look at this. This is more efficient. Do you guys understand that? Okay, so we'll answer that question. Okay, so, all right. They have exceptionally long and strong Achilles tendons. Okay, so there's the Achilles tendon for the kangaroo. And what this does is it's a very strong rubber band. It stores energy. So here's a kangaroo landing, and as it's landing, this tendon stretches. Okay, as it's landing, this muscle pulls on it, and the tendon stretches. It's like you've stored energy in a spring. And then when it jumps back, most of the energy stored is given back to the jump. Okay, these tendons recycle 90% of the energy from one hop to the next. Evolution favored this because it So kangaroos live in an environment where they lived in an environment of vast open place with sparse food. To get food, you had to travel a long distance and so on. And the food was sparse, so you had to adapt to this thing. Okay. Well, so it gives you that advantage. So why not still adopt this? It turns out that hopping is good in flat, open environments. If you have uneven terrain, you got to make turns and so on. Hopping is not a good strategy. Okay. And this thing with hopping, you need a So hopping puts repeated high loads on the tendons and knees and hips. Okay. So structurally there you have to be very strong, and kangaroos don't get knee replacement surgery. Once they're gone bad, you're done. Okay. All right. So these tendons, okay, so the tendons store energy. These tendons act like elastic bands, storing energy when the kangaroo lands and releasing it to propel them forward during hops. Okay, so you're getting back 90% of the energy that is stored there. Yeah. So tendons act largely as springs. Okay, your tendons act like springs as well. And muscles act primarily as tension generators. Okay, so let's understand this. Okay, so when the kangaroo is landing, the muscle is contracting, it's stretching the tendons. Okay, and you're storing energy, which is released back in the next hop. Okay. Terrestrial mammals experience higher metabolic rates when they run faster. So your rate of energy consumption is higher when you run faster. So kangaroos, macropods are capable of hopping at greater speed without incurring significantly higher energy expenditure. Okay, this is not actual data. This is just illustrative data, but data shown as illustrative. So in running, energy cost increases with speed. Hopping is most efficient at high speed, but less efficient at low speed. Okay, so at low speed, where did the graphs go? So at low speeds, hopping is less efficient. So kangaroos, when they're going at low speed, they start walking. So they're smart. Okay. So small wallabies switch to walking when moving slowly. Okay. So running, so here's why we chose running. Running offers better stability and control when changing directions, okay? Especially on uneven grounds. Okay? Hopping commits the body to large ballistic leaps. So when you're jumping like that. You can't change directions in midair. Okay? So you're committed to that. Okay? And in addition, runners can carry loads. Okay, you can carry your baby and run away from predators and stuff like that. Okay? While maintaining efficiency, hoppers experience strain when carrying extra weight. Okay, so kangaroos couldn't carry a backpack with load, even though. So they've evolved a pouch which still limits loads compared to bipeds. Running spreads impact forces across both legs. Okay, so when you're running, you're always only on one foot at a time. Okay? Hopping puts repeated high loads. Okay? So running animals can climb. It's versatile and navigate dense forests more easily. So if kangaroos lived in dense forest, of course, they'd be walking rather than hopping. Okay? So hopping is best suited to open landscapes and not dense rocky environment. So hopping is extremely efficient. So in summary, extremely efficient for large animals covering long distances and high speeds on open lands. Running is more versatile, better at low speeds, turning, carrying loads, and handling varying terrains. Okay? So in summary, the reason we walk is because this is where we spend most of our lives, at low speeds, okay? And our terrain dictates that we evolved to walk. Okay. The 3 or 4 times in your life when a lion chases you, you're willing to spend the extra energy running. Okay? All right, now we'll switch gears. We'll learn Newton's third law. So here's an interacting system. Here's the hammer interacting with the nail. Okay. And Newton's third law says, for every action, there's an equal and opposite reaction. Okay. So what does that mean? So if this hammer exerts a 10-pound force on this nail, the nail is exerting an equal and opposite force of 10 pounds. Okay. So what does the force that a hammer exerts on the nail do? Then it drives the nail into the wall. What does the force that the nail exerts on the hammer do? What does that do? The hammer stops. You've hit the hammer had a velocity when you were hitting the nail, and what's stopping the hammer? It's the force that the nail exerts. Okay. All right. So this is in this example. This is the environment. This is the system. Okay. For every action, there's an equal and opposite reaction, and that's Newton's third law. All right, now we'll define mass and weight. Mass is the amount of stuff that is in you. Your weight is, see, Earth is exerting a gravitational force on you. This force is directed towards the center of the Earth. Okay, and the magnitude of this force is your weight. Okay, so for instance, the force exerted on you here is there. If you were there, the force is in this direction. The force is always towards the center of the Earth. And your weight is just the magnitude of this force. So mass describes the amount of matter in an object. Mass is measured in kilograms, and it's an intrinsic property of the substance. So your mass won't change for instance, if you went to the moon. But if you went to the moon, your weight will change if you went to the moon, because the moon doesn't pull you as hard as the Earth is pulling you. Okay. So weight, however, is a force. Specifically, it's a gravitational force exerted by the planet. Okay. So for instance, on the moon, so the your weight is given by your mass times the acceleration due to gravity on the planet you are on. Okay. On the moon, the acceleration due to gravity is 1/6 that on Earth. Okay. The acceleration due to gravity on the moon is 1/6 that on Earth. So on the moon, you weigh 1/6 that on Earth. Okay. Of course, your mass is still the same. By the way, on the moon, astronaut John Young jumped 2 feet straight up, even though he was wearing that space suit that was weighed 180 pounds. So 2 feet is roughly this height. You could jump straight up. I looked up just coming before, Michael Jordan jumped 42 inches, 3.5 feet straight up. So by the way, so we use these various units. 1 pound is 4.5 newtons. Newtons is the SI unit for weight, for forces. Okay. And here's a mass to weight equivalent. Yeah. So let's say you go to Europe and stuff like that, you'll express your weight in kilograms, your mass in kilograms. So 1 kilogram is 2.2 pounds. Okay, what is your weight? Your weight is whatever planet you are on, the force with which that planet pulls you. attracts you. Okay. What is your apparent weight? Okay, so let's say I'm standing, my weight is 165 pounds. Why am I not going inside being pulled into the earth?
You said the earth is pushing you?
Yes, so the ground, the molecules on the ground are pushing me up. Okay? So when you're standing on the ground, so here's this fellow, there's his weight, the floor of the elevator is pushing him up. And that is your apparent weight. Okay? The force with which something is pushing you up, the contact force is pushing you up, that's your apparent weight. Okay. So right now you're sitting on the chair. If you're 165 pounds, what is the force with which this chair is pushing you up? It's 165 pounds. Okay. All right, that's your apparent weight. And that changes depending on the situation. So we'll talk about that. So for instance, so let's say I stand on a scale. The earth pulls me with a force of 165 pounds. And so the scale has to push me up with a force of 165 pounds. And so that's what it measures. Okay. Now we'll do the same experiment underwater. Okay. Again, the earth never quits. It's pulling me with 165 pounds. What happens underwater?
Buoyancy?
Buoyancy. There's a buoyant force. If you're underwater, the water pushes you up. And it turns out that we are essentially water. Our density is roughly the same as the density of water. And the buoyant force is roughly 165 pounds. Okay, so this force is canceling this force. So now the scale doesn't have to push me anymore. Your apparent weight underwater is 0. Okay, so you're weightless underwater. Okay. So the weight of the object is the force of gravity on the object. Gravity is not the force that you feel or sense directly. Your sensation of weight, how heavy you feel, is due to contact forces supporting you and the response of your vestibular system and to any motion. The vestibular system is in your inner ear that provides your brain with information about motion and spatial orientation. So your apparent weight is a combination of those two. And so when you're still, it's just the contact force that's pushing you. So when you sit on a chair, your sensation of weight is due to the normal force exerted on you by the chair. When you stand, your contact force of the floor pushing you against your weight is your apparent weight. So your apparent weight is the magnitude of the supporting contact forces. Yeah. All right, so what this diagram shows you is, here's an elevator accelerating upwards. When an elevator is accelerating upwards, see, gravity is pulling him down, and the force with which the floor pushes you, this force has to be greater than that so that the net force can accelerate you. So when an elevator is accelerating, you feel heavier. Okay, so you get on an elevator and it starts going up. As soon as it starts accelerating, you feel heavier. When it's going at constant velocity, then this force is equal to that, and your apparent weight is equal to your actual weight. Okay? So apparent weight can be measured by a scale. Whatever the scale reads, that's what your apparent weight is. Okay. Astronauts, when they're launched in rockets, they can experience quite large G's. So for instance, and when they slow down, when they're during re-entry and all, they can experience 6 to 7 G's. What that means is they're feeling 6 to 7 times heavier than their normal weight. Okay. And you got to train for that kind of stuff. Much of the thrill of amusement park rides, such as roller coasters, come from rapid changes in your apparent weight. Okay, so this force that the seat on your roller coaster pushes you up, that changes rapidly. Okay, so let me show you how that changes. So here's a roller coaster, let's say. Now, before I tell you this, I gotta. Okay, so we remember. So let's say you're going around in a circle at constant speed. Are you accelerating?
No.
So your speed is constant. Are you accelerating? Yes or no? There's only two choices. We have a no. No? All right. So velocity is a vector. It has both magnitude, which is your speed, and direction. And you see when you're going in a circle, your direction is changing. So you are accelerating. Okay. And the acceleration is pointed toward the center of the circle. This is known as centripetal acceleration. Okay. And the magnitude of this centripetal acceleration is your speed squared divided by r, the radius of the circle. So you see, the faster you're traveling in a circle, the greater your acceleration. The smaller the circle, the greater your acceleration. So it's very hard to go on a circular path a small radius. You need a large force. Okay? So something needs to push you when you go in a circle. You need this much force. All right, now we'll apply this to roller coasters. Yeah. All right, so let's say here's a roller coaster. All right, so down here, so if you were not moving, here's your weight, and the normal force is equal to your weight. Yeah. But if you're moving fast, now if you're moving, so if this were your velocity, if you're going fast, now this force, the normal force, has to balance your weight, and in addition, to make you go in a circle, you have to give a centripetal force as well. So this force has to become large. Okay. So when you're going on a roller coaster, when you get at the bottom, your apparent weight is quite large. Okay. And they can make you go fast enough where your apparent weight can be 2 or 3 times your body weight. All right, let's come up to the top now. If you're not moving, here's your weight, and here's your apparent weight. Okay, but if you're moving, okay, then you're going in a circular path. You need a centripetal force. Okay. You need a centripetal force, and the weight is providing that, and this normal force becomes smaller. So you can move at a speed such that the weight is providing the centripetal force, and you would feel weightless at the top. So you see, at the bottom of a roller coaster ride, your apparent weight is large. Here it can go to 0. And see, this rapid change in apparent weight is what makes a roller coaster exciting. Yep. You can experience this in a merry-go-round as well. And that happens sort of fast. At the bottom, you feel the heaviest, and at the top of the merry-go-round, you feel light. What's that? Sorry. Do you guys want to feel weightless? So I can tell you a trick to feel weightless. What? So if everybody wanted to feel weightless, all you have to do is, okay, so if you could ride this and not throw that, during that parabolic journey, you would feel weightless. So if we could get Hulk Hogan to come pick up this room and just throw it, while we're in flight, we'd all be weightless. Okay.
You put the flight on 0 G.
What's that?
You put the flight on 0 G.
Oh, Oh, you,
They do a parabolic flight pattern, you can do microgravity, etc.
Or you
yes.
can go in essentially deparation chambers.
Yes, so here's what our friend just said. So if you go on a parabolic trajectory, so if you throw a baseball, that if an object is free falling or moving only under the influence of gravity, this is the trajectory it goes on. Yeah. So you can fly a plane like this on a trajectory like this, and as long as it's on a parabolic trajectory, you'd be weightless. By the way, do you guys recognize this guy? That's Stephen Hawking. Yeah, so this lasts about 30 seconds. Okay. And so when they're training, they do several of these guys. I don't know, 15, 20 of those. And by the way, there are clubs at Riddle where students get to do this. Yeah. All right, so let's talk about that. So apparent weight. So much the thrill of amusement park rides is because of change in apparent weight. So buoyant force, our sensation of weight is altered when we are submerged in water, and this is relevant because there's plenty of life that lives underwater. You feel lighter when you stand in a deep pool. That's because of the buoyant force. Change in your sensation arises because of, in addition to gravity, you have the buoyant force. So the reduced apparent weight is the reason why many water-dwelling animals have soft bodies. So you don't have to be structurally as strong. All right. So now we'll talk about weightlessness. Okay. So what is weightlessness? When you do not feel any apparent weight. Your apparent weight goes to zero. Okay. So when an elevator is at rest or moving at constant velocity, so if the elevator is at rest, your apparent weight is equal to your actual weight. Okay. If you're accelerating upwards, this force has to be greater than this. If you're accelerating downwards, this force has to be less than this force. So your apparent weight will be less than your weight, actual weight. Okay? So here's another way to feel weightless. When you're feeling weightless, that means this force has gone to zero. So if you're in an elevator, and if the cable holding the elevator up gets cut, if the elevator free falls, during that fall, you'd be weightless. Okay? And that's the same thing as picking this room up and throwing it. So while the room is riding in air, you're weightless. So when an elevator accelerates upwards, you feel heavier. When it accelerates downward, you feel lighter. So if a man is in an elevator that's in free fall, so an elevator, you cut the cable, and if you stand on a scale in the elevator that's free falling, the scale will read zero. Okay? If you jump up in such an elevator, you'll just go to the ceiling. The same as if you've seen videos of people in International Space Station, it'd be just like that for the 2 or 3 seconds that the ride lasts. So if imagine an elevator that is in free fall, the man feels weightless relative to his environment, which is the elevator. Okay? Yes, so to be weightless, you need to be free falling. Free falling meaning gravity is the only force acting on you. So when you're on a parabolic trajectory, gravity is the only force acting on you. In level flight, there's lift and gravity. Okay? And so you're not weightless. So this is free falling. So you need to be free falling. So when the acceleration is 0, that's your normal weight, apparent weight is normal weight. When you're accelerating upwards, your apparent weight is greater than your actual weight. When you're accelerating downwards, your weight is less than your real weight. And when you're free falling, your apparent weight is 0. So when astronauts stand in an International Space Station, their apparent weight is 0. Okay?
Is the free fall term basically like at terminal or accelerating towards terminal velocity?
Free fall just means the only force acting on you is gravity. That's all. Okay? So right now, what are the forces acting on you? Gravity is acting on you, but there's the forces of the ground. How do I eliminate the force of the ground? If I drop the room,
Yeah.
and I would fall at the same rate as the room, and the room won't exert any forces. Earth. Okay, so why do the astronauts feel weightless in space? Okay, Earth's gravity has not disappeared in space. Gravity holds the space station in orbit. Remember, when the space station is going in a circular orbit, it's going at constant speed. The International Space Station is going at 8 kilometers a second. 8 kilometers is from here to State Road 40. Okay? But you see, so it is accelerating, and so the force of gravity provides the centripetal force. Yeah. So here, let me show you. Okay, so here's the motion. So here's a pen. That thing fell off the table, right? What happens if I shoot it faster? What will happen? It will go further, right? Can I shoot it such that it never hits the ground? Can I throw it such that it never hits the ground? What's that? No?
You would have to have enough velocity to leave the atmosphere.
I could. If I shoot it at 8 kilometers a second, it would never hit the ground. It is falling at the same rate as the Earth is curving. And that's what this International Space Station is. If I shoot it at greater than 8 kilometers a second, what do you think will happen? It will gain elevation. If I shoot it at more than 11 kilometers a second, then it'll escape Earth's gravity. Okay? All right, so that is what's happening. Okay. An astronaut, like a projectile, is continuously falling. Okay? And is following a curved trajectory. That was a curved trajectory when that object fell. Okay? So again, since I'm recording this, when you shoot it, there's a curved trajectory that the object goes on. This is a parabola. It's a parabolic trajectory. Okay? She doesn't fall out of orbit because her large speed allows the curvature of her trajectory to match the curvature of the Earth. So that's what's happening. So astronauts inside the space station, what is the only force acting on them? Gravity. They're in free fall, and so you feel weightless. So objects undergoing projectile motion travel in a parabolic trajectory or in free fall. NASA has these specially adapted planes that fly in trajectories for about 30 seconds. So each of this parabolic arc lasts about 30 seconds. So So Mr. Stephen Hawking, Professor Hawking got to experience this. Okay. So we interact with surfaces. You're interacting with the surface, the ground. Now, when you interact with the surface exerts two forces. Okay? It exerts a normal force, and it can exert a friction force. A force that is perpendicular to the surface, and a force that is parallel to the surface. Okay? And so this normal force is your apparent weight. Okay? And this friction force is useful for many things. Okay? So the locomotion of an animal or vehicle involves an interaction with the ground. Static friction force prevents your foot from slipping as you walk and propels you forward. Okay, so what we're saying is, and we mentioned this before, okay, when you walk, so when I'm walking, I'm pushing back, okay, and if my foot slipped, if there was no friction, then I couldn't walk. I couldn't go anywhere. So I'm relying on friction. So I'm pushing back, and that friction force is what's propelling. Okay, and we'll talk about, there's two kinds of friction, static and kinetic friction, and we'll talk about that in a little bit. Okay. Static friction force prevents your foot from slipping as you walk and propels you forward. So surface interactions are normal forces and those that are parallel to the surface. Okay, so perpendicular and parallel to the surface. So now we'll mention this. So when you have arthritis, so here's a normal knee that's filled with fluid there, and here's cartilage around the bone. You don't want bone rubbing against bone. And so your body is pretty amazing. This kind of shock absorption and all is built to last a lifetime. Okay, but for some reason, if these cartilage wear away, then when the bone rubs against bone, that can be painful. And this is when you need replacement surgery. So osteoarthritis results when the protective cartilage on the ends of the bone wears down over time. And that's painful. So osteoarthritis leads to joint pain, tenderness, and stiffness, and loss of flexibility. Okay. Rheumatoid arthritis is slightly different, even though the symptoms are the same. See, rheumatoid arthritis is an autoimmune disease in which the body's immune system attacks the synovium, the lining of the membrane, the synovium, the lining of the membrane that surrounds the joint. So here's the joint. It causes chronic inflammation along with joint pain and swelling. Okay. So rheumatoid arthritis and osteoarthritis are different. Again, the result is higher friction, which causes pain. Okay. All right, so let's do friction. We'll talk about friction now. Okay. So here's a box sitting on the ground. Okay, now let's okay, so what's happening here? Oops. Okay, what's happening? This guy is pushing the box with a force of 30 newtons. Why is the box not moving? I'm sorry? There's a friction force in the opposite direction. And so it's not moving. And how large is the friction force? That's equal to the applied force, 30 newtons. Okay? How large is the friction force now? 0. Okay? How large is the friction force? See, it's changing. It's equal to the applied force. And when the object is not moving, so you're pushing it in that direction, and if there was no friction, the object would move in that direction. So the friction force is in the opposite direction of the tendency to move, and it's a static friction force because the object is not moving. So for instance, if you had it stood on this side and pushed in that direction, the friction force would be in the opposite direction. Okay? So friction forces are denoted by the small letter f. And the S, the subscript S, tells you it's a static friction force. And you just saw that the static friction force can be 0. If you're not pushing on the object, the static friction force is 0. And it can be anywhere from 0 to a maximum value. Why is there a maximum value? Well, you can push it hard enough where it starts moving. Okay? So if you did this over here, you will find that the maximum static friction force so you can see that I've applied 110 Newton force and it's still not moving. So the maximum static friction force is greater than that. Okay, I need to apply a force greater than that. And for this setup, I believe it's 125 Newtons. So it started moving there. Okay, so the maximum static friction force was around 124 Newtons. Okay. Okay, well, what does that have to do with us? Okay, the maximum static friction force determines how fast you could run. Okay. Everything else being the same, if you wanted to run faster, what would you have to do? You'd have to have soles that give you the maximum static friction force. Have you guys seen any of this anywhere? I'll give you an example. Have you guys seen drag racing, where they go a quarter mile? These cars go a quarter mile, and you got to get there as fast as possible. You got to accelerate as fast as possible. What is it that they do before they go down that track?
Friction.
They burn their tires. So the tires get more sticky, and they can accelerate faster. Okay. All right. So the static friction force is the force that a surface exerts on an object to keep it from moving. Okay? So when you're pushing that way, there's the force. The static friction force is preventing you from moving. And here are the other two forces, the weight of the object and the normal force. Yeah. So the static friction force is less than, this is the maximum value. Okay, this is called the coefficient of friction, static friction, and that tells you how sticky the two floors are. Okay, and the normal force is, so if an object is just sitting on the floor, the normal force is equal to its weight. But if you push down on the object, then the normal force will become bigger. Okay, so the maximum static friction force is just equal to mu s times the normal force. So there is a maximum static friction force between two surfaces, and the maximum static friction force is given by that formula. So if you apply a force greater than the maximum static friction force, then it'll start moving. Okay? Once it starts moving, once the object starts moving, now there's a kinetic friction force. There's a friction force still. Okay, but this force is constant. And this kinetic friction force is always smaller than the maximum static friction force. So once you get it moving, then it's easier to keep it moving. Okay? So getting an object moving is the hardest part. And then once you get it moving, then you don't have to apply as great a force to keep it moving. And that's what these numbers tell you. So This is the static coefficient for rubber on concrete. Here's the kinetic coefficient for rubber on concrete. Okay. So what these numbers tell you is, I'll give you a specific example. If a 100-pound rubber block is sitting on concrete, what this number means is, so if the weight is 100 pounds, you need 100 pounds to get it started, to get it moving. Okay, that's what that number 1 implies. And to keep it moving at steady pace, what would you need? You need 80 pounds. Okay, so once you get it started, you need a smaller force to get it moving, to keep it moving. Okay. So those coefficients tell you how sticky the surfaces are. Okay. So there are 3 kinds of frictions we'll talk about: static friction, kinetic friction, and rolling friction. You see, rolling friction, coefficient of rolling friction is much smaller than kinetic friction. So here in this thing, so if you wanted to transport some stuff, okay, you put it in a cart. Here are bags that you're trying to transport. Here's the ground. What you do is you push, and you're working against friction. So you're working against this guy. Now, a few years ago, you got smarter, and what did you do? You invented wheels. And now, when you're rolling, the friction force is suddenly so much smaller. Okay? So life got easier. Yep. All right, so now here what we'll try and understand in this diagram is, again, so like I said, when you walk, what is it that you do? How do you walk? You're pushing against the ground, and the static friction force is preventing your foot from slipping, and that's what's propelling you forward. Okay, I can do this here on this carpeted floor. Could I do this on an icy floor or a smooth floor? Why not? So I don't know if you've experienced this, but when you're walking on ice, what do?
You slip.
You take small steps. Okay, so the reason you take small steps is the following. Okay, an icy floor can only provide you a small, the maximum friction force it can provide you is quite small. And that is because max is mu s times the normal force. And on an icy floor, this is small. This stickiness is small. This number is small. So it can provide you a very small maximum static friction force. Okay, so when I'm pushing on the ground, that's the force my leg exerts. This part of the force is balancing the normal force, my weight. Okay? This part of the force, if this part of the force became greater than this force, then my foot would slip. So this angle has to be small. And so you can only take small steps, because you can't make this component of the force greater than that, you would slip. Okay. So if the floor was frictionless, if this was 0, the force with which you can push has to be straight down. You could not walk. And you know that. So if the floor was frictionless, this force that you push with has to be straight down, and you couldn't walk. Okay? So since the static friction force has a maximum value for 2 surfaces, so it can be shown on concrete. On concrete with normal rubber boots, you can walk such that your foot angle this angle is 45 degrees. And on icy surfaces where the static friction force is that small, you can only walk with an 8.5 degree. This angle has to be 8.5 degrees. So giving you small steps, okay? So kinetic friction force is once it starts moving, then the friction force is the kinetic friction force. And the kinetic friction force, again, is given by this coefficient of friction, mu k times the normal force. Okay. And this number, mu k, is always smaller than mu s. Okay. So what this means is, once an object starts moving, you don't need as large a force to keep it moving. To get it started is harder. The kinetic friction force is smaller than the maximum static friction force. It is easier to keep an object moving than to get it started. The kinetic friction forces are independent of the velocity of the object. So this friction force is independent of the velocity, no matter how fast the object is moving. And the direction is always opposite to the direction in which the object slides across. So if the object is moving in this direction, friction force is like that. If the object is moving in this direction, the friction force is in that direction. When a wheel rolls, the wheel deforms, and you see there's these greater normal forces, and a result is a rolling friction force in the opposite direction. Except that the rolling friction force, this number is very small compared to, so mu r is much smaller than kinetic friction force, which is smaller than the static friction force. Okay, that's why it's easier to roll an object than to slide it across a floor. Okay. A wheel rolling on a surface also experiences friction. Rolling friction acts very much like kinetic friction, but is smaller because this number is much smaller. Yeah. It's easier to roll something on wheels than to slide it. Okay, so if you want to move some heavy object which doesn't have wheels, what do? You put rollers, lift it up, put rollers underneath it, and then move it. Again, that's how probably the Egyptians that built the pyramids did. Okay. All those huge rocks must have been moved through using rollers. So what causes friction? Okay, so what causes the friction between your foot and the floor? Okay, no matter how smooth a surface, it's pretty rough at a microscopic level. Okay, so these points that contact, they form loose bonds. Okay, so when I'm trying to push my foot, those bonds are pulling in the opposite direction. Okay, and even when you're walking, you're breaking those bonds, and that pull is what's causing the friction. Okay. All surfaces, even though they're quite smooth, are very rough to them on the microscopic scale. When two objects are placed in contact, so my foot is on the ground. So here's an interesting fact. Okay, so if you add up all this area of contact on my foot, the total area of contact would be roughly the size of the tip of this pen. Okay. So, when two objects are placed in contact, the high points on one surface become jammed against the high points on the other surface. The low points are not in contact. Only a very small fraction, typically 1/10,000th of the surface area, is in actual contact. So 1/10,000th of the area is in contact. Okay. Now, the amount of contact depends on how hard you push. So if I jump and land, the area of contact went up. Okay. For an object to slip, you must push hard enough to overcome the forces exerted with these contact points. Once the two surfaces are sliding against each other, the high points undergo constant collision, deformation, and even brief bonding that leads to the kinetic friction force. Okay. All right, guys, so we will stop here.